A stone heavier than 10 elephants once traveled across entire landscapes. This was the daily work of ancient engineers who built wonders like Stonehenge without modern tools. We are exploring the hidden logistics behind transporting megalithic stone along rivers and coasts. You will learn how our ancestors moved mountains of rock using only their wits and the world around them. How did they load a multi-ton block onto a wooden boat without sinking it? What secret knowledge of rivers and tides guided their way? This story reveals a forgotten chapter of human ingenuity that still holds powerful lessons for us today. What does it truly take to move a mountain? A master stone worker's hands moved across a granite outcrop, feeling for the story written in the stone. They were not just looking for a rock. They were searching for the one perfect block hidden within the mountain, a partner for an epic journey. This was the true beginning, long before any movement could start. The ancient engineers were masters of geology. They could identify specific rock types like sarsen, bluestone, or limestone, knowing which offered the ideal marriage of immense durability and just enough workability. They needed a stone that would not shatter under its own weight during transport, yet could still be shaped by their tools. Their eyes scanned the rock face for nature's own guidelines, the natural fissures and bedding planes that ran through the stone like hidden seams. Then they used a brilliantly simple technique. They would drive dry wooden wedges into these small cracks and then soak the wood with water. As the wood swelled, it created immense controlled pressure, forcing the rock to fracture cleanly along a predetermined line. This method minimized back-breaking labor and, most importantly, preserved the stone's internal integrity. Consider the specific spotted dolerite that forms the iconic bluestones of Stonehenge. This was not a local material. It was quarried from the Preseli Hills in Wales, over 150 miles away. It was chosen for its unique composition, a hard, crystalline rock that could withstand the trials of a long and difficult voyage. Why would they go to such extraordinary lengths for one specific type of stone? The answer lies in the immense challenges of the journey ahead. A weaker stone would never have survived. The granite block now lay free from the earth, a colossal shape resting in a cradle of stone and soil. But its freedom was only the beginning. Teams of workers would have surrounded it, their tools not of iron but of stone and bone. With heavy stone mauls and picks fashioned from the strong tines of deer antlers, they began the painstaking work of rough shaping. Every unnecessary pound of rock had to be removed. This was not about creating a perfect finish that would come much later. This was pure logistics, a brutal calculation of weight versus mobility. By chipping away the most irregular protrusions, they could transform a wildly shaped boulder into a simpler, more manageable form, one that might slide or roll or be lifted with greater ease. In ancient Egypt, the evidence of this practice is carved directly into the bedrock at places like the Aswan quarries. There, you can see the precise trenches workers cut around a giant obelisk, leaving the magnificent stone connected to the earth by just a single, slender keel of rock until the very moment it was ready for its journey. This preliminary shaping at the quarry was a brilliant strategic move. Why drag an entire mountain when you could move a refined piece of it? The monolith was now prepared, a sleeping giant ready to be awakened. But the quarry was often a confined space, far from any water or easy path. The first meter of movement was perhaps the most difficult, demanding a solution as simple as it was powerful. The true challenge began the moment the stone left its cradle of earth. Now a roughly shaped monolith, it had to traverse that first brutal mile from the quarry to the waiting water. This overland prelude was a symphony of coordinated effort, a battle against friction and gravity. Envision a massive wooden sled, its timbers groaning under the weight of a stone heavier than several elephants. It does not roll on wheels but inches forward on a track of carefully laid logs. Teams of hundreds, sometimes thousands, of laborers pull on thick ropes made of hemp or leather, their voices rising in a unified chant to synchronize their immense effort. The ground before the sled is not solid earth but a slick path of wet clay or mud, meticulously watered by other workers to drastically reduce friction. This was the reality of the terrestrial haul, a grueling but essential operation. In places like ancient Egypt, we find evidence of elaborate mud brick ramps coated with slick slurry, engineered pathways designed for one purpose, to coax a giant down to the river. On Rapa Nui, a different kind of ingenuity emerged. Oral traditions and modern experiments suggest the island's famous moai statues might have been moved in a rocking, upright motion, made to walk by teams rhythmically tugging on ropes from either side. This method would have allowed a small group to maneuver the massive heads across the island's landscape. Success in this phase was not about speed, it was about relentless, sustained momentum. Every inch gained was a victory. The successful arrival of the stone at the riverbank or coastline was a monumental achievement, a celebration earned by sheer human perseverance. But this hard-won milestone only presented the next, even more delicate puzzle. How do you convince a floating piece of wood to accept a passenger that wants to sink it to the bottom of the river? The riverbank presented a problem of pure physics. How do you transfer a stone that weighs many tons from solid ground onto a floating platform without capsizing the vessel or losing the stone to the murky depths? The solution was as clever as it was nerve-wracking. Workers likely constructed an earthen ramp that extended from the bank into the water, sloping gently down beneath the surface. The massive barge, empty and riding high, would be maneuvered directly over this submerged ramp. The stone, already resting on its wooden sled, was then carefully inched down the slope until the sled's leading edge met the barge's deck. With painstaking control, the teams would have continued pulling, using the barge's own buoyancy as a counterweight. As the stone slid further onto the deck, the vessel would sink lower into the water, its immense displacement capacity finally being put to the test. This was a slow-motion ballet of force and balance, a moment where one wrong move could spell disaster. The groan of timbers and the tense silence of the workers would have been the only sounds marking this critical transition from land to water. Once the stone was centered and the vessel stabilized, it was no longer a rock on a boat. It had become one single, monumental entity, ready for its journey. The simple act of loading was a testament to an intuitive understanding of principles we now call physics, all achieved with ropes, ramps, and raw human determination. Now, with its precious cargo secured, this specialized craft was ready to face the water. But the river itself held its own set of challenges, demanding a different kind of knowledge from its captains. The groaning of the sled timbers was replaced by a new sound, the rhythmic slap of water against a wooden hull. Loading a megalith onto a waiting watercraft was a moment of supreme tension, a ballet of controlled chaos where the stakes were absolute. One wrong move, one snapped rope, and the entire endeavor could sink to the bottom of the river. One prevalent method was as straightforward as it was nerve-wracking. Workers constructed an earthen or wooden ramp that sloped from the bank down into the deeper water. The empty barge, moored securely, would be positioned directly at the ramp's end. Then, with teams hauling on multiple ropes to control the descent, the massive stone on its sled was inched slowly down the slickened ramp and directly onto the deck. As the immense weight transferred, the boat would sink lower and lower into the water, its buoyancy fighting the load until a precarious equilibrium was found. Another, more elegant technique might have employed the principle of the lever. Imagine a counterweight system, much like a giant shadoof used for lifting water. A long, pivoting timber could have been used to gently swing the stone from the bank and over the water, lowering it with far more control than a simple slide. For coastal transport, the very ocean itself became a tool. Barges could be intentionally grounded on a gentle shore during high tide. While the vessel sat stable on the exposed seabed, the stone was laboriously moved aboard. Then everyone would wait. As the tide rolled back in, it would lift the now loaded barge, refloating it effortlessly. This method required an intimate knowledge of the lunar cycle and tidal patterns, but it turned the immense power of the sea into a willing accomplice. Every one of these loading operations demanded precise timing, a deep, intuitive understanding of buoyancy, and a workforce that moved as a single, disciplined entity. Success meant the stone was no longer a separate burden. It had become part of the vessel itself, and with that fragile union secured, the true voyage, a journey across the ever-changing moods of river and sea, could finally begin. With the stone secured on its vessel, the journey entered its most fluid and unpredictable phase. This was not a battle against the water, but a delicate partnership with it. A flotilla of heavy-laden barges, often without a single sail or oar, drifted with the river's current. The crews were not rowers but pilots. Their main tool was a long pole, used to fend off from the bank and steer the clumsy craft away from hidden snags and sandbars. Rivers provided a natural highway, but they were a highway with their own rules, demands, and moods. Success required a sophisticated, almost intimate knowledge of hydrology. Transport crews planned entire expeditions around the seasonal floods. These annual deluges were not disasters to be feared, but opportunities to be seized. The higher water levels submerged dangerous shoals, lifted the barges over obstacles, and created a wider, deeper channel for the massive stones to pass through. They learned to read the river's language, using the main, powerful flow in the center of the channel for propulsion, while expertly avoiding the treacherous, swirling eddies along the banks that could spin a barge out of control or dash it against the shore. Coastal voyages operated on a different clock, the rhythmic pulse of the tides. Here, the immense power of the moon itself was harnessed. A barge could be towed into position by smaller boats on a rising tide, using the incoming water's energy to carry it forward. Then, at a predetermined spot, it would be settled onto a prepared bed as the tide receded, sitting perfectly in place for unloading when the water fell. This passive propulsion strategy was a stroke of genius, conserving immense human energy and turning the environment itself into the primary engine for movement. Yet for all this cleverness, navigating these watery paths was a constant negotiation with danger. A sudden summer storm could turn a placid river into a raging torrent. A hidden underwater rock, invisible from the surface, could tear open a hull in an instant. The journey was a calculated risk, a testament to human courage backed by deep, hard-won knowledge of the natural world. The lead pilot stood at the bow, his entire being focused on reading the river's secrets. His eyes tracked subtle swirls on the surface, his ears tuned to the sound of water flowing around a hidden snag. Navigating a stone-laden barge was an art form passed down through generations, a deep, intuitive map of the river held not on parchment but in memory. He knew that a certain pattern of ripples meant a sandbar was building just beneath the surface, while a change in the water's color signaled a deep, safe channel. His primary tool was a long pole, constantly dipped into the water to measure depth, calling out soundings to the crew who used oars or ropes from shore to make minute adjustments to their drift. This was not a journey of speed but of precision. Every bend in the river was a known entity, every fallen tree along the bank a familiar landmark. In more complex environments, like a river delta merging with the sea, this knowledge expanded into a coordinated system. Smaller, faster boats might scout ahead, placing simple marker buoys to define a safe passage, or guides would be stationed onshore to signal the best route through the treacherous, shifting waters. The pilot's role was the most critical link in the chain, a human gyroscope balancing the immense, inert weight of the stone against the living, unpredictable force of the water. His correct judgment meant progress. His single error could mean catastrophe, sending a monument destined for the ages to a silent, muddy grave. This profound reliance on localized expertise raises a compelling question. How did these ancient societies organize the monumental effort required to feed, house, and coordinate the hundreds of hands needed for such an undertaking? This human river of labor, the thousands of hands that pulled the ropes and shaped the ramps, was itself a monumental construction. The true engine behind moving these stones was not just ingenuity, but a breathtaking feat of social organization. Think of it as a vast, mobile city dedicated to a single purpose. This was a society in motion, a complex hierarchy that transformed chaotic individual effort into a symphony of coordinated power. At the top were the master engineers, the architects of the impossible. These were the individuals who could calculate the buoyancy of a barge, design a riverbank ramp, and chart a course using the stars and the seasons. Their knowledge was the project's blueprint. Beneath them were the overseers, the foremen of the ancient world. Their role was one of relentless coordination, translating the engineers' grand designs into actionable commands for the teams on the ground, or rather, in the water and on the bank. They were the ones ensuring that the rope makers produced cables strong enough, that the carpenters built sleds that would not splinter, and that the path ahead was cleared and prepared. Then came the immense body of the workforce itself, the quarriers, the haulers, the pilots, and the countless support roles. This was not a disorganized mob. It was a disciplined machine with teams specialized in specific, brutal tasks. The rhythmic chant that synchronized the pull on a rope was not born of spontaneity. It was a practiced drill, a metronome for muscle. The popular image of slaves being whipped into building the pyramids is being steadily dismantled by archaeology. Evidence from workers' tombs and settlements near Giza, for instance, points to a rotating labor force of conscripted Egyptians. These were often farmers who worked on these colossal projects during the inundation season, when the Nile flood made their fields untouchable. They were not slaves, but citizens contributing to a national, perhaps spiritual, endeavor. And they were cared for. Excavations have revealed bakeries capable of feeding thousands, evidence of medical care for injuries, and settlements that provided shelter. The logistics of feeding this army alone was a nightmare of its own. Just imagine the supply lines, the constant flow of grain, fish, and beer required to fuel such immense physical exertion day after day, month after month. This intricate social pyramid, with each layer supporting the one above it, was the true foundation of every stone circle, every obelisk, every monument that seems to defy explanation. It was a collective agreement, a shared burden that turned the dream of a temple into a reality of stone. A fallen tree, invisible just beneath the surface, was one of the river's deadliest traps. The current would funnel water through its tangled branches, creating a powerful suction that could pull an entire barge under in moments. This was the brutal reality of river transport, a journey where every bend could conceal a new crisis. A logjam or a beaver dam could appear overnight, transforming a clear channel into an impassable wall of wood and debris. The solution was as physically demanding as it was straightforward. The crew, armed with stone axes and ropes, would have to dismantle the obstruction piece by piece, or in some desperate cases, they might even partially unload their own vessel, lightening it enough to be dragged over the obstacle. For more permanent challenges like rapids, their engineering genius shifted to the river itself. They constructed temporary wing dams, walls of stone and timber built out from the banks to narrow the river's flow. By concentrating the water into a single, deeper channel, they could subdue the whitewater and create a calmer, safer passage for their precious cargo. In times of severe drought, when the water level dropped too low, they faced their most difficult choice. They could wait for days or even weeks for the rains to come and replenish their liquid road. Or they could take matters into their own hands, digging temporary side canals to bypass the shallowest sections, a back-breaking effort that moved earth instead of stone. Every mile was a negotiation, a test of patience and raw problem-solving skill. The river provided the power, but it was human resilience that ensured the stone reached its destination. The open sea was a different kind of monster entirely. Where the river offered a predictable current, the coast presented a chaotic dance of wind and waves, a realm where a stone-laden barge was at its most vulnerable. These vessels, designed for displacement over speed, were ungainly giants in the face of the ocean's raw power. Their freeboard, the height of the deck above the water, was perilously low, and a single large wave could wash over the side, threatening to swamp the entire craft. Every coastal voyage was a carefully calculated risk, undertaken only during the most placid months of the year when the sea was known to sleep. Pilots clung to the shoreline, using the familiar shape of the land as both their map and their potential salvation. A sheltered cove or a river estuary was not just a landmark, it was a promised safe harbor should the weather suddenly turn. To aid their progress, these barges might have been fitted with simple square sails, catching a favorable wind to ease the burden on the teams of rowers in accompanying boats who strained at their oars, towing the behemoth forward. But the sail was a fickle partner. An unexpected shift in the wind could turn it from an asset into a liability, pushing the clumsy vessel toward the very rocks they were trying to avoid. The ever-present threat was a sudden squall, a summer storm that could blow in from nowhere, churning the sea into a fury that would easily overwhelm a low-sitting barge. To embark on such a journey was an act of profound courage, a testament to a faith in their own skill and the mercy of the elements. Successfully navigating a coastal passage was one of the journey's greatest triumphs, a hard-won victory that meant the stone was finally within reach of the sacred site it was destined to crown. The final sight of the quay did not signal the journey's end, but its most delicate and dangerous climax. This landing site was no simple riverbank. It was a carefully engineered gateway, a platform of stone or reinforced wood built to withstand the final, crushing weight of the monolith. Here, the entire river voyage culminated in a single, precise operation, unloading the stone without disaster. The process mirrored the initial loading, but with one critical difference: the need for perfect placement. The barge, now weary from its journey, was carefully maneuvered against the quay's sturdy pilings. Teams on shore would have prepared an earthen ramp leading from the water's edge up to solid ground. Just as before, they might have used a slick layer of mud to reduce friction, creating a controlled slide for the colossal cargo. With painstaking care, ropes were attached and teams began the slow, agonizing pull to coax the stone on its sled from the deck of the barge onto the ramp. This was a moment of supreme tension. The vessel, relieved of its burden, would lurch upwards in the water, and the stone would begin its final terrestrial journey. For some monuments, like the Moai of Rapa Nui, the process was even more dramatic. Oral histories and archaeological experiments suggest the statues were not laid flat, but were carefully offloaded in an upright position. Using a rocking motion and a coordinated system of ropes, teams could have made the Moai walk from the landing site to its ahu, or platform, a breathtaking spectacle of human control over immense stone. This final transfer demanded the same brutal coordination and intuitive engineering as every step that came before. One misstep, one rope snapping under the strain, could shatter the monolith or send it tumbling into the water, rendering the entire epic journey a total loss. Success here meant the stone was finally home, ready to be raised into the sky and take its place in eternity. The story of Stonehenge's bluestones is a saga written in stone and water. These iconic pillars, quarried from the Preseli Hills in Wales, began an epic 140-mile journey to the Salisbury Plain, a logistical masterpiece that pushed ancient engineering to its absolute limits. After their initial overland haul, the stones faced their first major waterway. Teams maneuvered them onto waiting barges along the rivers of the Bristol-Avon system. This was not a gentle float trip. The journey downstream would have been a tense piloting exercise, navigating currents and avoiding hazards before emptying into the vast and unpredictable Severn estuary. Here, the true test of coastal navigation began. The estuary is known for its powerful tides and shifting sandbanks, a place where a loaded barge was at its most vulnerable. Successfully crossing this coastal stretch required impeccable timing and a deep respect for the sea's moods. From there, the stones likely moved inland once more, traveling up the River Avon in Wiltshire. This final river passage brought them closer, but the last leg was still to come, another grueling overland haul to the sacred site itself. This entire route is a perfect case study, a seamless fusion of every method we have explored, from the brute force of land haulage to the clever use of river currents and the daring of coastal sailing. Why would a civilization commit to such a staggering effort for stones that were not even local? The answer must lie in something far greater than mere convenience. The bluestones were not just building material, they were likely sacred, their unique origin and properties imbued with profound spiritual meaning, making the entire monumental journey not a burden but a pilgrimage. The Egyptian obelisks stand as the ultimate expression of megalithic ambition. These were not merely large stones, they were polished needles of red granite, some weighing over 400 tons and stretching 100 feet towards the sun. Their journey began in the specific quarries of Aswan, where the unique, flawless granite was prized above all else. Once a single, perfect obelisk was freed from the bedrock, it faced the longest water voyage of any megalith we have discussed, a trip of hundreds of miles down the very spine of Egypt, the Nile. For this, the Egyptians built not simple barges but colossal, dedicated transport ships. We have depictions of these vessels from temple walls, showing them as vast, bloated hulls dwarfing the fleets of smaller boats that surrounded them. These were the tugs of the ancient world. Dozens of rowing boats, each with a crew of 30 men, would have been harnessed to the main barge with thick ropes, their synchronized strokes providing the motive power to maneuver the sluggish giant. The Nile itself was the perfect partner in this endeavor. Its predictable, gentle current offered a natural south-to-north highway, while its annual inundation was the key that unlocked the entire operation. The Egyptians planned their transport missions for the height of the flood season. The higher water submerged sandbanks and riverside obstacles, creating a wider, deeper channel for the massive barge to pass through safely. It was a perfect synchronization of human effort with the natural calendar, but the true climax of the operation occurred upon arrival. At a temple complex like Karnak, the obelisk was unloaded not onto a quay, but directly into its final position. Workers constructed a vast V-shaped ramp filled with loose sand. The obelisk, still on its sled, was carefully pulled up this ramp until its base was positioned directly over the waiting foundation stone. Then, in a moment of breathtaking precision, the sand was slowly excavated from ports at the bottom of the ramp. As the sand drained away, the obelisk descended in a perfectly controlled slide, its base guided into a small depression until the monolith stood upright for the first time. This entire process, from quarry to raising, was a state-level operation of unimaginable scale. It required the coordination of thousands of workers, the management of immense resources, and an unshakable confidence that such a thing could even be done. The obelisk was more than a monument. It was a statement, a declaration that human will, when perfectly organized, could command the very earth and the river to its purpose. A thick rope woven from countless fibers of hemp was the strongest tool in their entire arsenal. This was technology built on a human scale, a material so simple yet so vital it could mean the difference between a stone moving and a stone sinking. The true heroes of these epic journeys were not complex inventions, but the absolute mastery of basic materials. Rope, wood, and the fundamental principles of physics were the engines that powered the impossible. These ancient engineers were masters of materials science long before the term existed. They knew that a rope's strength lay in its unity. Individual plant fibers like hemp or papyrus, or even strips of leather, were weak on their own. But twisted together into ever thicker cables, sometimes as thick as a man's arm, they created a single entity of immense tensile strength, capable of withstanding many tons of pulling force without snapping. Wood was their other great partner. It was not just a single material to them, but a versatile palette. Heavy, dense timbers like oak were chosen for the keels of barges and the runners of sleds, where crushing weight and abrasion were constant threats. More flexible woods were selected for levers which needed to bend without breaking under immense strain. They understood the grain of the wood, working with its natural strengths rather than against them. Their greatest genius, however, lay in applying simple machines. The lever was a fundamental tool, a long, sturdy timber placed under a stone's edge, with a pivot point and a team of people pushing down on the far end, could generate enough force to lift a corner that no number of hands could move directly. This allowed them to shift the stone's weight, to reposition sleds, or to make minute adjustments during the perilous loading process. The inclined plane, in the form of their earthen ramps, turned an impossible vertical lift into a manageable, gradual slide. And the roller, a series of logs placed under a sled, transformed sliding friction into the far lesser rolling friction. Each time the sled moved forward, the rollers left behind would be carried to the front, creating a continuous, renewable track. This was not magic. It was an empirical, hard-won understanding of mechanics. They knew instinctively how to distribute weight, how to reduce friction, and how to amplify the force of 100 people into the power needed to move 1,000 tons. There were no cranes, no engines, no power sources beyond human muscle and the current of a river. Their achievements seem even more profound because they are built from concepts we can all grasp. It forces us to reconsider what is truly possible when human ingenuity is paired with the simplest of tools and an unwavering collective will. The success of a megalithic voyage depended as much on the calendar as it did on engineering. Ancient project managers were masters of scheduling, their grand plans dictated by the immutable rhythms of the earth and sky. They did not fight the seasons, they rode them like a current. For river transport, the most precious window of opportunity was the annual flood. In Egypt, this was the inundation of the Nile, a predictable, life-giving event. Across Europe, it was the spring snowmelt swelling rivers into powerful, broad highways. Launching a stone-laden barge at the peak of these high waters was a strategic masterstroke. The deeper channels submerged dangerous shoals and allowed the massive vessels to float over obstacles that would have grounded them in the drier months. They were harnessing the landscape's own power, letting the planet itself do the heavy lifting. Coastal voyages operated on a different but equally predictable schedule. The open sea was a benevolent partner only during the calm, stable weather of summer. To attempt a passage in autumn or winter was to invite disaster, risking the entire cargo to the storms that churned the waters into a fury. This careful timing extended beyond the elements to the very people who made it all possible. These monumental projects were often staffed by a rotating labor force of farmers. The same hands that sowed and harvested crops were conscripted for public works during the agricultural off-season, when their fields lay fallow. This was a brilliant societal adaptation, ensuring a massive workforce was available without crippling the food supply. The entire operation, from quarry to coast, was a synchronized dance with the environment. It was a profound understanding that human ambition could only be realized by listening to the world, by moving with its flows and respecting its tempers. This deep connection raises a final, humbling thought. What have we lost in our modern era of controlled environments and constant, year-round construction? The sheer scale of this labor force points to an even deeper mystery: the colossal economic engine required to set these stones in motion. Moving a single megalith was an undertaking of astronomical cost, a financial burden that could only be shouldered by a powerful, centralized authority. A pharaoh, a king, or a high chieftain commanded the state's entire treasury, drawing upon the wealth gathered through taxation, the tribute paid by conquered territories, and their absolute control over lucrative trade routes. This was not a community fundraiser, it was the full weight of a kingdom's economy mobilized for a single purpose. The most fundamental expense was food. Just imagine the endless river of grain, fish, and beer required to fuel thousands of workers performing backbreaking labor, day after day, for months or even years. This required a massive agricultural surplus, a society productive enough that it could divert a significant portion of its harvest away from its villages and into the mouths of its monument builders. We see the physical evidence of this support system etched into the desert at Giza. The remains of workers' villages there are not simple camps. They are small towns with industrial-scale bakeries and breweries, facilities capable of producing food for an army of laborers. Beyond sustenance, the project consumed raw materials at a staggering rate. Forests were felled to provide timber for sleds, barges, and ramps. Quarries for stone tools operated non-stop. Rope makers needed a constant supply of hemp or papyrus. Potters produced countless vessels for water and food storage. The entire society became a supply chain dedicated to one goal. A ruler's ability to launch such a project was the ultimate flex of political and economic muscle. It was a very public declaration, a statement that said, "I command the labor of thousands, I control the wealth of the land, and I can bend our entire economy to my will to create something that will last for eternity." This was not just about moving stone, it was about cementing a legacy in the very fabric of the world. A single shouted command could not carry across the roaring effort of 1,000 workers. In an operation spanning hundreds of miles from the deep quarry to the distant temple site, the true nervous system was not muscle but communication. It was an invisible web of messengers and signals that bound the entire, sprawling endeavor into a single, coordinated entity. Imagine a runner, breathless, arriving at a river, landing with a crucial message carved on a clay tablet or knotted into a string. The quarrymaster reports a delay. A stone is taking longer to shape. This news must race ahead to the transport captains, telling them to hold the barges, to recalculate the entire schedule based on the tides. A single piece of miscommunication, a message lost or misunderstood, could create a domino effect of disaster. A barge might arrive at a shallow river section to find the winged dams not yet built, or a hauling team might wait for days for a stone that was never freed from the earth. For shorter distances, visual signals provided an instant, synchronized pulse. On a riverbank, the lead overseer might raise a colored banner. The instant it dropped, teams on both sides of the river would heave on their tow ropes in perfect unison, guiding the barge through a narrow channel. At night, the flicker of a single fire on a hilltop could be a prearranged signal to a flotilla waiting offshore, telling them the coastal conditions were safe to approach. But for the grand design to hold, everyone had to speak the same technical language. The master engineer's vision had to be translated into actionable commands that a quarrier in Wales and a barge pilot on the River Avon could both understand without error. This required standardized units of measurement. A cubit was not just any forearm's length, it was a specific, agreed-upon distance. When the plan called for a stone 10 cubits long, every worker at every stage of the journey knew exactly what that meant. A common technical vocabulary was just as vital. The terms for a lever, a roller, a sled runner, or a specific type of rope knot had to be universally understood. This shared language prevented the chaos of misinterpretation and ensured that a complex instruction from the central planner was executed with precision by a crew that might be weeks of travel away. This web of communication, woven from runners, smoke, fire, and shared words, was the fragile, vital glue holding the impossible together. But how can we be sure these daring reconstructions hold any truth? Our most powerful evidence comes not from ancient texts, but from modern hands getting dirty. This is the world of experimental archaeology, where scholars trade their books for tools to test these theories in the real world. They build scale models in university labs and, more impressively, full-scale replicas in open fields and on real water. They are not just imagining the past, they are physically rebuilding it, one heavy lift at a time. A landmark experiment took place on Rapa Nui itself, where a team attempted to move a concrete replica of a Moai statue. Using a system of ropes and a coordinated rocking motion, they successfully made the massive head walk upright across the landscape. This hands-on trial proved the method was not only feasible but also remarkably efficient, turning a local oral tradition into a validated engineering principle. Similarly, researchers have constructed reed boats based on ancient designs and loaded them with multi-ton stones to see if they would remain buoyant. The results often shatter our assumptions. A seemingly simple theory might collapse under the actual weight of the stone, while a method written off as folklore might prove startlingly effective. These practical trials reveal the hidden failure points no blueprint can predict. They show us how a rope truly frays under days of strain, or how a wooden sled behaves differently on wet clay versus dry sand. This process transforms abstract calculations about travel speeds and labor crews into tangible, physical data. We learn not just how it could have been done, but how it likely was done, through a process of trial, error, and ultimate triumph that echoes the very experiences of the ancient engineers themselves. Each stone possessed a soul, a life force that needed to be guided home. This was the profound belief that transformed backbreaking labor into a sacred pilgrimage. The journey from quarry to temple was never just a matter of logistics. It was a reenactment of a mythological story, a symbolic transition from the raw chaos of nature to the divine order of civilization. The quarry was a place of primal power where the stone slept within the earth. To extract it was to awaken a slumbering giant, to invite its spirit to join the human world. The route it traveled was not chosen for mere convenience. Often, it mirrored the symbolic pathways described in their oral traditions. perhaps tracing the journey of a founding ancestor or a revered cultural hero. Every river crossed and every hill climbed was a step along a preordained spiritual map. The immense labor itself was a form of communal worship. The rhythmic pull on a rope, the unified chant of a hauling team, these were not just techniques for efficiency. They were acts of devotion, a physical prayer offered by an entire community. The shared sweat and strain forged a powerful collective identity, binding everyone from the master engineer to the newest laborer to a purpose far greater than themselves. In this light, the motivation becomes clear. Why would a society commit generations and vast resources to move a mountain? Because they were not moving inert rock. They were escorting a divine ancestor or channeling the power of a god into a permanent home. The stone's final placement at the sacred site was not the end of a construction project, but a spiritual awakening, the moment the captured essence of the land was activated for the benefit of all. The logistical triumph was merely the physical manifestation of an unshakable faith. A snapped rope echoed like a thunderclap over the river. In that single, catastrophic instant, years of planning and backbreaking labor hung by a thread. For ancient engineers, disaster was not a remote possibility. It was a constant companion on every journey. Their true genius lay not just in making things work, but in planning for when they would inevitably fail. This was a world built on redundancy. For any critical lift, they never relied on a single rope. They used multiple, independent cables so that if one frayed and snapped under the immense strain, the others would hold, preventing a total collapse. Their entire operation was a mobile workshop, carrying spare parts as vital as the tools themselves. Extra wooden rollers were always on hand to replace those crushed under the weight. Stone mauls and levers were stockpiled, ready to step in when a primary tool shattered. This was not wasteful. It was a profound understanding that materials have limits and that planning for breakage was the only way to prevent a permanent halt. Before attempting a dangerous maneuver like guiding a barge through a treacherous set of rapids, they likely ran drills. They might have practiced the entire sequence with a smaller, less valuable stone, a test run to identify hidden currents and perfect their coordinated signals before risking the real monument. This practice transformed unknown dangers into manageable procedures. The social structure itself was the ultimate contingency plan. A project employing thousands could absorb a localized disaster. If a sledge broke, there were always more carpenters to repair it. If a hauling team fell ill, another could be rotated in. This immense scale provided a resilience that a smaller operation could never muster, allowing them to treat delays and setbacks as temporary obstacles rather than existential threats. Their success was forged in the expectation of failure, a lesson in perseverance that echoes across the centuries. A snapped rope on Easter Island would not have doomed a moe, just as a sudden drought on the Nile would not have halted an obelisk forever. The true lesson of megalithic transport lies not in a single master blueprint, but in the stunning diversity of solutions born from unique landscapes. These cultures all faced the same brutal physics, yet their answers were as distinct as their homelands. On the remote island of Rapa Nui, the Polynesians carved their moai directly from the volcanic rock of a single quarry. Their world was an island with no vast rivers to exploit. Their solution was almost entirely terrestrial, a breathtaking feat of balance and coordination. Oral traditions and modern experiments strongly suggest they used a rocking motion, making the statues walk upright by teams tugging on ropes from either side. For longer distances, they likely employed wooden sledges or log rollers, moving the giants along prepared tracks that crisscrossed their small, isolated world. Their genius was in mastering the land itself, Far across the ocean, the Inca of the South American Andes faced a different kind of terrain, a world of staggering mountains and steep valleys. They too were terrestrial masters, but their environment demanded a different kind of ingenuity. They moved massive, often irregularly shaped blocks of andesite for their sublime structures at sites like Sacsayhuaman. Their methods relied heavily on earthen ramps, levers, and an immense labor force. They would build extensive ramp systems to haul stones up mountainsides, using log rollers and ropes made from tough local grasses. The Inca prioritized fitting stones together with impossible precision at their destination, a technique that reduced the need for long-distance transport of perfectly shaped blocks. Their focus was on overcoming vertical elevation, not navigating watery highways. This stands in stark contrast to the civilizations of Western Europe and Egypt. These cultures were defined by their rivers, the Nile, the Avon, the Seine. For them, water was not a barrier, it was the answer. They invested immense resources in building specialized barges and mastering the hydrology of their arterial waterways. Their engineering marvels were floating ones, designed to let the current do the work that thousands of straining muscles would have to do elsewhere. This comparative view reveals a profound truth. There was no single secret, no lost universal technology. The real secret was human adaptability. Each culture looked at the world around them, assessed the materials at hand, and applied a brilliant, localized logic to achieve the impossible. The Polynesians solved the problem with ropes and rhythm, the Inca with ramps and relentless effort, and the Egyptian with barges and the flood cycle. They all reached the same pinnacle of achievement, but they climbed there on entirely different paths. The echoes of these ancient endeavors did not fade into silence. They resonated through the centuries, forming a hidden bedrock for the engineering marvels that followed. The organizational genius and practical physics mastered by megalithic cultures became a vital inheritance, a playbook for moving the massive. The Roman Empire, with its vast bureaucracy and disciplined engineering corps, was a direct heir to this legacy. They transported Egyptian obelisks across the Mediterranean to adorn their capital, employing the same principles of barge design and river navigation, but on a staggering, imperial scale. Their ability to coordinate the quarrying, shipping, and erection of these monoliths was a direct evolution of the systems pioneered thousands of years earlier. Later, the master masons of the medieval cathedrals faced a similar puzzle: how to lift and position immense blocks of stone high into the air. Their solutions, encoded in the secret knowledge of guilds, relied on the same fundamental tools: the lever, the winch, the inclined plane, and the coordinated labor of thousands. The soaring spires of Chartres or Notre Dame stand as a testament to this unbroken chain of practical knowledge. Even the Industrial Revolution, with its iron horses and steam engines, was built upon this ancient foundation. The great canal systems and transcontinental railways of the 18th and 19th centuries were, at their core, solutions to the same age-old problem, moving immense weight across daunting distances. The only thing that changed was the power source, swapping human and animal muscle for steam and steel. The intellectual toolkit itself, the mindset that breaks an impossible task into manageable steps, that understands friction and leverage, and that can command the effort of thousands toward a single goal, was forged in the quarries and on the riverbanks of prehistory. This continuity forces us to see a direct line from the first team that dragged a sarsen stone across the plains of Wiltshire to the crews that laid the tracks across a continent. The modern world was not born in a vacuum. It was built stone by stone on the wisdom of the ancients. A snapped rope in the ancient world was a disaster, but a broken theory today is a breakthrough. We are living in a new golden age of discovery, where our most advanced tools are finally allowing us to test the grand stories of megalithic transport with hard, tangible data. Ground-penetrating radar now sends pulses deep into the earth, painting a picture of the subsurface without a single shovel breaking the ground. It can reveal the ghost of a prehistoric trackway, a path worn smooth by the passage of countless feet and heavy sledges, now buried under centuries of soil. Even more powerful is LiDAR, or light detection and ranging. When mounted on an aircraft, this technology can digitally strip away dense forest canopies to reveal the true lay of the land beneath. It has uncovered the subtle contours of lost causeways and, critically, the faint, meandering scars of silted-up river channels that were the true superhighways of the ancient world. These are not just lines on a map, they are the rediscovered arteries of a forgotten transportation network. Meanwhile, in the laboratory, geochemists are playing a high-stakes game of match the stone. By analyzing the unique chemical fingerprint of a megalith from a site like Stonehenge and comparing it to samples from known quarries, they can now trace a bluestone not just to a specific hill in Wales, but to the very outcrop where it was born. This precise sourcing rewrites our understanding of trade routes and cultural connections, proving with scientific certainty the incredible distances these stones traveled. And what of the engineering challenges? Powerful computer simulations can now model the immense stresses on a hemp rope during a controlled descent down a riverbank ramp, or calculate the exact buoyancy and stability of a hypothetical barge design under different wave conditions. These digital experiments allow us to fail safely, to see which methods would have worked and which would have ended in a catastrophic loss. This technological revolution does not replace the archaeologist's trowel or the historian's intuition. Instead, it provides a powerful new lens, turning speculation into evidence and giving us our clearest view yet of the brilliant, practical minds who first dreamed of moving mountains. A rope could snap, a barge could sink, but the most fragile component in the entire operation was the human spirit. After months of backbreaking labor, a worker might look at the half-finished stone ramp and know with absolute certainty that he would never see the final pillar raised into the sky. His children might not even witness it. The psychological endurance required for such an undertaking is almost beyond our modern comprehension. This was not a sprint, it was a generational marathon run at a brutal pace. The project managers understood that you cannot feed morale with bread alone. The true sustenance for this long-term effort was a powerful, unifying belief system. The work was not just a job, it was a sacred duty, a direct contribution to the cosmic order. Each stone set in place was a prayer made solid, ensuring the sun would rise, the river would flood, and the kingdom would prosper. This shared faith transformed exhaustion into devotion. Charismatic leaders, whether a revered pharaoh or a visionary high priest, acted as the living embodiment of this purpose. Their presence on the riverbank, witnessing the struggle, solidified the connection between the grueling daily task and the glorious, eternal outcome. The workforce was not an anonymous mob, but a structured society with its own rhythms of reward and recognition. Rituals and festivals marking the completion of a major phase, like successfully loading the first barge of the season, would have broken the monotony and reinforced communal bonds. A skilled quarrier or a pilot who navigated a treacherous rapid might earn marks of distinction, a special tool, or an extra ration of beer, granting them status among their peers. This created a culture where excellence was visible and celebrated. The very act of participating, of pulling on that shared rope, forged a powerful collective identity. A worker could return to his village and speak with immense pride of his role in building the eternal temple, a story that would be told to his grandchildren. The project's immense difficulty was paradoxically the source of its psychological power. Overcoming each setback, from a snapped cable to a sudden drought, reinforced their shared resilience and the righteousness of their cause. They were not just moving stone, they were proving their worth to the gods and to history itself. The movement of megalithic stones was one of humanity's grandest early experiments in large-scale logistics, a breathtaking symphony of human ingenuity, raw labor, and deep environmental wisdom. This was not a series of disconnected tasks, but a single, flowing operation that stretched over years, sometimes generations. Every single step, from the master stoneworker's first touch in the quarry to the final, nerve-wracking slide onto the quay, was a calculated maneuver in a complex and beautiful dance. It was a dance with physics, a dance with the river, and a dance of thousands of souls moving in perfect, coordinated rhythm. These staggering achievements force us to shed the outdated idea of primitive ancestors. They were, in fact, brilliant problem solvers who looked at a mountain and saw not an obstacle, but a partner. They mastered their world not with magic, but with an intimate,